Hello, this is Greg Partika, and I would like to show you a simple modeling tool that we've made available via the Open Geosolutions website. It lets you define a layering profile and a wavelet shape, then examine the impedance and reflectivity responses in both time and frequency. In this way, it is very much like our other block filter web app, but here we have the added benefit of allowing you to examine the effect of spectral color on the responses. Layer stacking patterns, that is the geology, can be represented by reflectivity or by impedance. The geological content remains exactly the same in both cases, but the spectral color of reflectivity is different from the spectral color of impedance. The reflectivity case is richer in higher frequencies. The impedance case is richer in lower frequencies. There have been a number of publications related to this concept. Key papers include Velzebuhr in 1981, Walden and Hoskin in 1985, and then Lancaster and Whitcomb in 2000. Let's look at a couple of cartoon illustrations to explain further. A filtered seismic reflectivity trace is made up of the reflectivity, or in other words, the geological content. What we're talking about here is the spikes that represent the impedance boundaries. So it's that plus the wavelet and noise. When we look at these components in the frequency domain, we see that the geological portion, that is the reflectivity, the part that we're most interested in, is not white or flat. It is blue, that is, it has stronger amplitude at higher frequencies and weaker amplitude at lower frequencies. The geological response can also be represented by impedance layers. The content remains the same as it was for reflectivity, but now we are representing the geology by layers or impedance blocks rather than by reflection coefficients that represent layer boundaries. Wavelet and noise considerations remain, but we see that the layering or impedance version of the geology exhibits a red spectral color, stronger amplitude at lower frequencies, and weaker amplitude at higher frequencies. So here, for example, we see amplitude spectra computed from a sample well log profile. At the top, we have log amplitude versus log frequency of the reflectivity version of the profile. At the bottom, we see the log amplitude and log frequency of the impedance version of that same profile. The unfiltered responses are in red. To show the effect of bandpass filtering, we applied a bandpass sync wavelet. That result is shown in blue. Application of a Texas double, or in other words a 2-octave high-end slope wavelet with minimal side lobes, is shown in green. As you can see, the reflectivity-based spectrum exhibits a blue spectral color. It is richer in high frequencies. The impedance-based spectrum exhibits a red spectral color. It is richer in lower frequencies. You can take any well log-based impedance profile and generate a reflectivity version of the same content, then compute amplitude spectra, one using the impedance as input and the other using reflectivity as input, and find that in general impedance profiles exhibit a red spectral color and reflectivity profiles exhibit a blue spectral color. Even though neither reflectivity nor impedance exhibit a white or flat spectrum, spectral whitening was historically accepted as a desirable shaping during seismic processing. Modules for performing spectral whitening remain available in many processing toolkits. Our Spectral Color web app allows you to examine reflectivity and impedance in both time and frequency domain with 3 cases of spectral color type. Red, which is impedance appropriate, blue, which is reflectivity appropriate, and also white or flat. On startup, the web app comes up with a default set of parameters, so you can simply hit the Submit button to see a go-by example. The profiles are defined by a series of time impedance pairs, for example as shown here. The first pair represents the background impedance and the start time of the first layer. The last time pair represents the end time of the last impedance block. The background impedance value is also assigned to times beyond the end of this last block. In this case, the impedance profile is a 2-layer case with a 4 millisecond hard layer, followed by another 20 millisecond hard layer separated by 6 milliseconds. The wavelet parameters are specified up above as either an Ormsby or a Ricker shape. The time and frequency domain responses can be viewed in both time and frequency domain with and without the presence of spectral color. If we define resolution according to the traditional view, that is using criteria such as peak to trough time separation or dominant frequency, then the filtered reflectivity version, which has the blue spectral color intact and shown here in cyan, appears to provide more resolution than the white with no spectral color filtered reflectivity version, which is shown in gray. Likewise, the filtered impedance version with the red spectral color intact, shown here in magenta, appears to provide less resolution than the white with no spectral color filtered impedance version shown in gray. But how can this be? The geological content is identical. The bandpass filter parameters are also identical. Well, it is the spectral color that is making the difference. The problem is that the traditional approach to resolution and detection makes no attempt to decouple spectral color from the wavelet shape. By incorporating spectral color as part of the modeling workflow and decoupling it from the seismic wavelet filter shape, we can better understand the impact of each component on the combined response. These individual components are the geological content, that is the local interference pattern controlled by the reflective target material, the spectral color, which is controlled by the choice of representing the geological content as reflectivity, which is blue, or impedance as red, and the seismic wavelet, which in our case we are defining as either an Ormsby or a Ricker wavelet. By being able to model the interplay between the individual components, we gain a better understanding of how each one impacts the ability to resolve or detect reflective material. So to recap, the purpose of this modeling tool is to 1. Construct a geological scenario, that is impedance or reflectivity profile, 2. To specify a filter shape, and 3. To view the band-limited response, that is the interference pattern in both time and frequency, with and without the presence of spectral color. And with that, I would like to thank you for your time and interest, and I hope you enjoy our spectral color modeling web app.